I wanted to share some work that my group has been doing over the past few years called proximal causal inference. Causal inference might be new to folks here, and this is a sales pitch. So I'm going to try to make a compelling case that this may actually be relevant for some of the work that you may be interested in pursuing, whether it's methodologically or in theory or in some of your applied research. My goal is by the end of this talk that we go past introduction, you understand what proximal causal inference is and how it potentially could apply to some of your work. So here's a quick outline of my talk. This talk is about confounding, also known as batch effects. And I promised myself to say batch effects as much as possible throughout the talk, as opposed to confounding. And I think of the two are very closely related, which is essentially on unwanted sources of variation, data that confounds the association that you're interested in learning about. And so negative controls are a very natural way to deal with hidden sources of bias. So I'm going to introduce negative controls for those of you who haven't seen them before. I will introduce them from the perspective of epidemiology. Okay, and negative controls have been used for a while, well before I even knew they existed. Initially in wet lab studies, but also more broadly even in epi, there were several applications over the years before we got interested in it, and we tried to formalize it as an area in statistics. Proximal causal inference, there I go back. Proximal causal inference is a particular implementation of negative control. Negative control is used to detect bias, and we wanted to go beyond that, and it will require additional assumptions, but we wanted to debias our inferences once we've detected bias, not just say we're unhappy with the inference, give up on your data, but rather are there particular sources of information, known nulls that you can actually leverage to remove bias. And then very briefly, I have one slide on potential extensions to other kinds of questions about the impact of interventions that arise primarily in public health, but also in the social sciences. So this is, by the way, it's a busy slide, but I'm going to go through it. It's supposed to be a review slide or an introduction to causal inference slide under the usual assumptions. And there's a little bit of notation here, but I'm going to narrate throughout. So the first bullet point here is introduces the notation that we use to communicate causal effects. So imagine you're an individual who has a headache and you're contemplating taking an aspirin, and Y little a is the outcome you would experience if you were to take treatment little a. So little a would be you take aspirin versus you don't take aspirin. We refer to a causal effect as a contrast between those two outcomes at an individual level, right? You imagine, even before whether you take the aspirin or not, you can imagine conceptually this exercise. I have an outcome if I took the aspirin, I have an outcome if I didn't take the aspirin. That's basically what we mean by causal effect, is that contrast. Obviously, you will make a decision at some point and it will reveal one of the outcomes, but not the other. The role of causal inference is to look at the data that you end up observing and try to infer the original potential outcomes, both of them, and learn about their contrast. Now, if we were to experiment, or we had the ability to run a randomized trial is essentially sampling, and so you would get a representative sample of both outcomes. People who are randomized to take treatment, you get the outcome on the treatment, which is representative of the outcome on the treatment for the entire population because of randomization. For those who are randomized not to take treatment, you'll get the outcome on the no treatment, which is a representative sample of the outcome on no treatment for everyone in the population. And you take that contrast, you get a causal effect. That's why randomized trials work, because they actually allow you to sample these potential outcomes. Today's talk is not about randomized experiments, it's about observational data. It's often impossible to randomize in public health and health sciences in general. Partly because of resources, limits on resources, but also because of ethics, right? That's often we're interested in causal impact of harmful intervention. Air pollution might be an example. We have a population that's exposed to air pollution, and we want to infer what would have happened to that population if we were to intervene and reduce the air pollution. That's not about the data you see. That's beyond the data you see. You want to imagine an alternative universe where you could actually intervene and remove the air pollution. This is not about contrasting people who had high level of air pollution to people who had low level of air pollution, because those two people, subsamples are not comparable in general, right? In terms of social demographics, in terms of aging, in terms of how people decide where to live, in a manner that would confound, that would create some kind of nonsense association between the two factors. All right, and so we're going to be interested in observational data, and we want to recover inference about a population average causal effect. So that will be the contrast between two potential outcomes, one under treatment, under control for each person, and then that average over the population. Okay, the first one is, what would happen to this entire population if I expose everyone to the intervention? What would happen to the population of Australia if everyone were above the age of 16 were forced to take a COVID vaccine? That's one outcome. And then you're interested in the simulation study where you try to infer what would have happened to the entire population in Australia if you were to force everyone not to take a vaccine, so you didn't approve a vaccine. That contrast is a causal contrast. And so this is not about comparing individuals who happened to take vaccine to individuals who did not. The target of inference is the population average causal effect, the average effect of the contrast of these two outcomes. The standard assumption that's made in the analysis of observational data, which we're going to try to challenge today and relax, is that in fact you've measured, you have observational data, you might have confounding, but you've measured all relevant factors, X. That is the standard method, that conditional on measured factors, pretreatment covariates, adjusting for confounding factors that you've measured, you can explain away confounding. And the way that's usually characterized is that essentially once I've adjusted for covariates, treatment is as good as randomized as by nature. 99% of papers on causal inference rely on this assumption. This is not a testable assumption. So the way it's usually encoded is that conditional covariates, your treatment is essentially generated by a coin flip. It might be a biased coin flip because it depends on your covariates, but it's independent of everything that's latent, all measured covariates. Potential outcomes, as I said earlier, you can think of potential outcomes as baseline covariates because we can define them even before I get to see the data. They're part of our beings. We have the two potential outcomes. What would happen to me if I took aspirin? What would happen to me if I didn't take aspirin? They're latent. It's a little weird to think about the symbol means they're independent conditional covariates. It's a little weird to think about potential outcome being independent of treatment if we're interested in the effect of treatment on the outcome. But this is not the observed outcome, this is the potential outcome. So this is an assumption that would in principle be guaranteed by an actual randomization. And so the standard assumption in causal inference, the standard assumption in epidemiology in general, is that you've measured enough factors to explain away the confounding. If one were willing to make that assumption, then the causal effect would become identified, and there are three ways to identify it, which means you can learn from the observed data, just like you would in a randomized trial, but you have to account for those covariates. And there are three standard ways of doing it. I have the acronyms here, inverse probability weighting or inverse propensity score weighting, and where you would measure, you would estimate from the data the propensity score for the treatment, which is denoted by PAX, and then you would apply a weight to everyone who happened to be treated, and this would adjust for the covariates. You could do the most standard thing that people will do would be to run a regression model. So you could run a regression model within the treated, within the untreated, conditional on covariates. This is what people typically do. But because we're interested in the population average causal effect, you would then standardize. So this expectation here is a standardization to get a population average causal effect, which allows for the presence of heterogeneity without necessarily trying to estimate heterogeneity. And then there is a third one known as AIPW, augmented inverse probability weighting, that includes both of them and has some kind of robustness property. I'm not going to emphasize that today. All right, so this is the standard. This is the state of the art in causal inference. There's a big problem, as I mentioned, which is this assumption of no measure confounding, that you've measured all relevant covariates that explain any spurious association between the treated and the untreated. So that's what we mean by confounding, that there are factors that are associated with both the treatment and the outcome that correlate the two because they're common causes. People who are sicker tend to get treated, right? Measures of morbidity are covariates that predict the outcome, how well they're going to do, their welfare. And doctors will typically treat people who are not doing well. So if you're not accounting for morbidity, you would have confounding. So the standard assumption is to assume that you've measured all those confounding variables. This is not a testable assumption. There's nothing in your data that will tell you that you're wrong without making an additional assumption. So today I'm going to talk about one such set of assumptions. That's what proximal causal inference is. We'll be able to assess whether or not there is bias in our analysis, in our observational analysis, that's due to spurious association, due to hidden factors. And eventually we'll be able to debias our estimate of association. And so we want to answer this question, can we establish a similar identifying formulas meaning that can we learn from the observed sample, can we make inference about causal effects in the presence of unmeasured confounding by hidden factors U associated both with treatment and outcome variables. Okay. And please do interrupt if something is not clear. Now for the next 30 minutes or so, I'm going to ignore measured covariates because this is going to be about hidden confounding variables. Okay, and so I'm backing up a little bit. That slide was really busy, and thank you for going through that with me. You think we have a basis now? I'm going to go slower now, and I want to introduce new ideas. Okay, so the new ideas are we're not going to rely on anything having to do with measured covariates X. So I'm going to just ignore the measured covariates. Imagine that you're conditional all of it, taking care of that. But that's not enough. There are unmeasured covariates that affect both treatment and outcome. So for instance, later on, I'll talk about an example where the treatment of interest is vaccination in the population after the vaccination has been approved. So there are observational studies to evaluate the effectiveness of the vaccination in the real world studies. We want to look at the effectiveness of the vaccine in preventing infection or severity of disease. And we worry about confounding. In these settings, the most important confounding, intractable confounding, is actually healthcare-seeking behavior. People who have a higher proclivity to think about their healthcare and to protect their healthcare will be more likely to get vaccinated. And we'll probably take more measures to prevent infection. That creates confounding. And this is notoriously hard to adjust for. So most vaccine studies have some degree of unmeasured confounding by healthcare-seeking behavior. And regardless of whether we adjust for the obvious confounding factors that are always observed, age and sex, and maybe also whether patients are immunocompromised, because then by indication you will get a vaccine. Those data are usually available. But underlying latent healthcare-seeking behavior is hidden, right? And so unmeasured confounding is good. I'm going to use U to refer to these hidden factors. And they are at the center of much skepticism about observational studies across the health sciences and, in fact, across social sciences as well. Whenever you get a study, recently I had this debate with one of my colleagues, with Armando, about the potential effect of GLP-1 in the population as opposed to in the randomized trials. And essentially, from observational data, the real debate is whether the side effects outweigh the benefits, and that we haven't actually observed the side effects because they haven't been around long enough, the long-term impact. This is not something that randomized trials are going to tell us anything about. This is evidence that's going to come from observational study. And you will be faced with a situation where we would have government agencies trying to monitor the overall adverse events of these approved drugs in the population. And they will do this so observationally and try to learn whether or not those are actually caused by GLP-1s. And then you'll have drug companies arguing that actually, no, they're not due to the GLP-1 drugs, they are actually due to confounding. Confounding is often cited as the reason why we should not trust observational studies. And so this is sort of like a glaring issue The same issue arises in a completely different area that I'm also interested in, which is in air pollution studies. Air pollution studies, at least in the United States and many other places in the world, are regulated via constant monitoring of the health effects of air pollution. Companies that industrial companies will often argue that the evidence doesn't warrant a change in regulation because it's not subject to a randomized trial. We'll never run a randomized trial for looking at the health effect of air pollution. So everything comes down to skepticism about the credibility of observational data in settings where a randomized trial will never be conducted. So today I want to argue that negative controls and proxies, these very simple tools that are often available in practice, are really a hidden treasure to both detect and potentially correct for this confounding bias and to make our studies more credible. Okay? So here's an example from the literature. This was a study by George Davis Smith, where he was interested in the causal impact of maternal stress on baby birth weight. Maternal stress during pregnancy, baby's birth weight. Okay? And so he found this huge association, and he wondered whether he could claim that was a causal association. He was adjusting for covariates as well. Okay? And the effect was larger than he expected. Right? He expected some level of interurine exposure that would lead to this such association to be causal. But he worried that there may be some nonsense association due to confounding. And so what he did, something very clever, he looked at paternal stress as a potential negative control. Now, this requires having a known null hypothesis that you know is credible. So the idea here is that paternal stress is likely to have a causal effect on baby birth weight. There is no biology that would suggest that such a direct effect would exist other than through maternal stress. All right, and so what he did is he ran a regression, and I'm hiding the other covariates here, but he ran a regression of the outcome, birth weight, on maternal stress and paternal stress. So he's adjusting for maternal stress. And the question is, does paternal stress still have an association? And the idea here is, upon adjusting for your covariates, if you find an association between paternal stress and maternal stress, it has to be due to a pathway that's not on this graph. There has to be another pathway in here. We're ruling out a direct pathway, therefore it has to be a confounding pathway, a non-causal pathway. And so which one is it that he worried about? He worried about family factors that could be on measured confounders. So environmental factors that equally affect both parents that could lead to confounding bias, and it's a confounder because it's a common cause of all the variants. And so using this simple tool of adding an observed variable you know should not be present, should not have a causal effect, and finding one indicates that you potentially have to worry about hitting confounding. This is it. This is basic idea of a negative control. It's very simple, right? And it's actually has two components. One component is this null association. Okay? This is not something that you can learn from the data because we're checking whether it's present. So you have to be very well grounded in whether or not it is credible that there is a direct effect, okay? That there is no direct effect. So that's the first component. The second component is that the negative control, this is what we'll refer to as a negative control exposure. The negative control exposure that they chose was one that was actually relevant for the source of confounding he was worried about, right? He wasn't worried about maternal stress from work, maternal stress during pregnancy from work. He was worrying about source of confounding that will equally affect the mother and the father in a general sense, maybe not on the same scale, but that these are environmental factors in the family lifestyle that will impact both of them. And so this is the choice of the particular negative control that he picked. It has to be relevant for the source of confounding. So this is not a magical tool. This is not about all sources of bias. This is about specific sources of bias. And the idea is, if you're familiar with observational data, it is customary to really think carefully about the potential source of confounding. So this is exactly the same thing. You have to think about potential source of confounding. You'll try to measure covariates to adjust for them. And what we're going to suggest is some of the covariates that we usually use can actually be thought of as proxies for the degree of confounding. Okay? And if that's true, then really we should think of them as ways to actually detect bias and potentially think of them as mismeasured versions of non-measured confounding. And this is the idea of debiasing. Measurement error has been a part of statistics for a long time. And so he's thinking about this problem as a measurement error problem, potentially. Okay, something that statisticians are very familiar with, understanding uncertainty due to measurement error. So there are different perspectives for the same idea. Here's a formalization of those two assumptions. Z will be referred to as the negative control exposure. If Z is independent of Y, conditioning on U and A, and I'm always implicitly conditioned on the measured covariance. And so that means that if I had measured all the unmeasured confoundings, there would be no association between Z and Y, conditional on A and U, right? If you measure all the unmeasured confounders and your negative control exposure does not cause the outcome, it would be rendered independent of the outcome, conditional on those unmeasured confounders. This is very similar to an assumption that's often made in measurement error, that if I had measured the underlying error-prone variable, right, the actual error-prone measurements would become rendered irrelevant to what I'm studying, right? It's a very similar notion, okay? So it's just a generalization, just to think more about tailoring it to think about causal associations. And so that null association is not because of a measurement error between Z and Y, but rather that Z is known a priori not to cause Y and is known to be relevant for U. Okay, I'm going to skip this. There's a class of method known as the strata variable methods that are often used to address similar problem with non-measured confounding, but I didn't describe them. I would just say, if you're familiar with them, you can think of IVs as a potential negative control exposure. So it's easier for you to come up with IVs. They're often, maybe the closest IV that might be familiar to this audience would be in Mendelian randomization studies. Genetic variants will often be used as IVs. And so the idea is that genetic variants in such analysis are actually negative control exposures. They can be repurposed in this fashion. And this is important because if you have multiple ways of thinking about a particular adjustment, you may have multiple ways of making an adjustment. That's in fact the case. There are multiple ways of using an IV. You can use them as an NCE as opposed to as an IV. And this is also useful because an invalid IV is also a valid NCE. And I'm not going to say more about that. I'm going to move on to talk about negative control outcomes. And I'm going to introduce negative control outcomes similarly to how I introduced negative exposure with a current example. This example is a completely different example. This is looking at a question that with a postdoc we were interested in answering, which had to do with the 2015 Zika virus outbreak in Brazil. And we wanted to know whether it led to a decrease in birth rate in Brazil. And so I have a picture of Brazil here. The hotspots for Zika virus was up here, right, northeast, and the southeast was not very affected. So what we did is we took a state up here as our treated unit, and we took all counties in that state as our units, and then a state that was not impacted as the untreated state, as the unexposed state. Will be more appropriate here. And we wanted to know whether or not there was a causal relationship between a drop of the rate of birth, the birth rate in Brazil that was associated with this horrible virus outbreak Brazil experienced in 2015. The whole world experienced it, but some parts of Brazil was heavily hit because of rainfall and the amount of mosquitoes that happened to be aligned with the outbreak. Okay. And so in this case, what we did was we were interested in so the Zika outbreak was in 2015. That's when the exposure occurred. And we had birth rate both in 2014 and 2016. We wanted to know about the Zika virus outbreak on birth rate in 2016. And the idea here was to look at birth rate in 2014 as a negative control outcome. And the idea here is that causal effects do not occur in reverse. There's no notion of causal effect affecting the past. They always affect the future. And so we can rule out a causal effect between Zika in 2015 and birth rate in 2014 before the outbreak occurred. And this is a notion of a negative control outcome, an outcome that is known a priori not to plausibly be causally impacted by the exposure. All right. The potential measure confounding that we're interested in detecting here were confounding factors that were region-specific, looking at healthcare infrastructure, socioeconomic status, cultural perspective on childbirth, but also meteorological features of the region. And so the idea would be to run a regression where you replace the original outcome, birth rate in 2016, you simply replace it with birth rate in 2014, adjust for your measured factors, and then look for an association between the outbreak and birth rate before the outbreak. We found such an association that would indicate bias. And so we've arrived at two parallel ways of detecting bias. One is using a negative control exposure, defined as a variable that would be rendered independent of the outcome, conditional on measured confounding factors and the treatment, and negative control outcome variable that would be rendered independent of the treatment. I will also include the negative control exposure here because we'll eventually use both. Conditional on the unmeasured confounding, we require both of them to be relevant for the unmeasured confounding. Relevant meaning that this arrow needs to be present. And so this is a selection criteria on how you might select a negative control variable in a given application. A pre-trained outcome is a really good NCO. In fact, there is a precedent for this. You might have heard of difference in differences. It's a very popular method that's used for situation where you have pre and post treatment measurements of your outcome. The Zika virus example was one such example. And so you can also think of a DID setting as a particular instance of such a negative control outcome. Due comparability, as I said, it is important to select NC and NCO that are associated with your source of unmeasured confounding. Okay, and this is no different than the way you will typically design a study, which is you would think about the potential source of confounding, and you try to measure factors that are associated with that source of confounding. The suggestion here is that we should not just adjust for it in the traditional sense, but we can actually leverage it in a very straightforward way to potentially detect for hidden confounding bias. If your negative control exposure and negative control outcome are irrelevant for the source of confounding, they will be completely useless. There is no magic here, they will be completely disconnected. And you might be fooled to think that there is actually no confounding because you'll find no association between either the treatment of interest and the NCO or between the outcome of interest and the NCO. And so this is a really important criteria. Fortunately, it's a criteria that in the presence of unmeasured confounding can be assessed empirically because such a confounding factor will introduce an association between the NCO and the NC. So by looking at an association between the NCO and NC would actually confirm the presence of unmeasured, the relevance assumption in the presence of unmeasured confounding. All right, so I'm going to skip this in the interest of time, but these are basically, we use DAGs to represent causal assumptions that one might make. You might think that this is a really strong thing to do. How do I know what the causal assumptions are? But it turns out that any statistical analysis we make has a corresponding causal story to interpret. And so this is simply encoding such a causal story, okay? And so when we do a statistical analysis, in order to interpret it causally, we have in mind a particular causal mechanism. So these graphs are very useful to write them down. The reason I have them here, I have two sets of such slides, is just to demonstrate that these assumptions that we need for the NCO and for the NCE, oops, where do I go back? Oh, I keep hitting. are really the assumptions that do matter. The graph itself doesn't matter, provided that those assumptions are satisfied. So the assumptions can be satisfied by different types of graphs. So let me just skip this in the interest of time. I have a couple of slides, I guess a few more examples of this, just to further illustrate that these are actually, these variables are often available in the data that we observe. So I mentioned earlier looking at the health impact of air pollution. So imagine that I'm interested in the air pollution on a given day, on health measurements on the next day. The typical, the canonical example of air pollution studies on the impact of air pollution on health are time series studies across different cities or across different states. At least in the US, it would be across different cities where the positioned air pollution monitoring devices, primarily focusing on PM 2.5, particularly matter of size 2.5, and looking at that are known to get into the lungs and cause all kinds of bad things, like aggravation of asthma, or also induce hospitalization in elderly individuals related to pulmonary diseases. And so we might have a time series data at the city level, where we look at the particular health outcome, like the ones I mentioned, and air pollution right before, and we're looking for acute effects. This is a typical, pick up any New England Journal of Medicine, they will have such a study that's published based on such observational data. That's the standard. That's what's being used by the EPA every year in the US to set the standard for air pollution. Okay? What's tolerable and what's not tolerable. And the idea there is, as I mentioned earlier, there's controversy around these studies due to the potential confounding that can never be ruled out, right? Because these are not experimental studies, so purely observation. So one might say that where people live and are exposed to more air pollution might also be associated with it, might also cause bad outcomes. Individuals who cannot afford the housing that's away from industrial areas might also experience bad outcomes due to their socioeconomic status and their general morbidity, right? These data often may not have the granularity at the individual level to be able to really appropriately account for such potential confounding. And so this is a potential vulnerability of the studies. So the idea here is actually that you don't need to think very far to think about negative control variables. One could easily come up with a negative control exposure and negative control outcome variable by using the time series formation. So what you might do is, like in difference and differences, you might use the health effect here in May 1st, which occurs before air pollution at the city level. Those measurements, these are time series at the city level, so you have these measurements. And so because it occurs before the exposure, it cannot causally be affected by the exposure. And because it's the same variable as the outcome, just measured at a different time point, if there's any confounding for the outcome of interest, it will also confound this variable. Okay, and so it's relevant, and it satisfies our null hypothesis that the treatment of interest or the exposure of interest cannot cause an impact. Likewise, I could use air pollution as an NCE. This thing, I think, is dead. Can you see the red dot?
Yeah.
You can see it? No. Okay. All right. I'm going to give up on that. Likewise, I could use air pollution the day after the outcome. So May 4th, the outcome is measured on May 3rd, as an NCE. And again, it's the idea that this air pollution on May 4th cannot possibly causally impact May 3rd. And so in these time series studies, you can essentially use crossover. This is a very simple crossover design type of design that's often used actually in epidemiology for other reasons. And you can use them to detect, and as I will see in a few slides, to also control for confounding bias. I'll try to stop myself. I'm not going to go over all my slides because, as always, I have too much stuff. But I do want to have some time for you to challenge some of my claims and to ask me really well thought out question. And I'll call on people if you don't. Don't fall asleep yet. Think of your question first. All right. The second example, which I actually be familiar with many of in the crowd, is actually in research studies. One is in genetic research and genomic research in general, one is often worried about batch effects. And usually it's standard to actually use control genes to remove unwanted source of variation. One of the very first papers that I actually read on negative control was one by Terry Speed, who of course is in Melbourne, and I visited Melbourne during this visit, only to find out that he was in the crowd. Suddenly I lost all my confidence. But he was very gracious and very kind and supportive, and so I appreciate that. And fortunately, I had cited his papers, and so all was good. But all control genes are a very old standard that some folks in the room have also actually written papers about, and essentially to detect such confounding factors that are not causal and be able to rule out such batch effects in genomic studies. And then finally, comparative effectiveness of the kind that I talked about earlier, safety studies where approved drugs are monitored for long-term side effects or safety signals. The concern there is that we don't want to miss anything that's incredibly, that may be harmful to the health of people, that have unintended consequences. And so those databases are typically enriched with other treatments and other outcomes. And we have a large project with the FDA now to automate negative control techniques to be able to empower such monitoring and prevent false negatives and make sure, in this case, we really don't want to miss anything that's harmful, as opposed to wanting to test a null hypothesis. And so negative control exposure and outcomes have become incredibly important in those settings. So hopefully, I'm not going to talk about I could talk ad nauseum about example, could be spend the next half hour doing so, but hopefully this was enough to convince you that these are important sources of concerns for public policy and public health decisions in practice. Just to reinforce that, I wanted to just give you a little bit of an outline on a number of references. Some of them are ours, but there are many others that I thought about this. On the evolution of negative control methods in the literature, they were traditionally used to detect for bias. At some point, they were shown to actually, in some certain conditions, to reduce bias. The idea is if you have a negative control, it's actually, in many cases, it's better to adjust for it as a covariate than not to. That you end up getting something that's between your bias estimates and the truth. And so that's what we call bias reduction or bias attenuation. But it does require some assumption. It's not a given. Those assumptions on whole can actually amplify the bias. So there were some papers about those phenomena, and then more recently, this is where we're focused, is looking at further assumptions where if you have multiple negative controls, how you could use them to actually recalibrate your inference and correct for confounding bias. And I have all the slides are available. I'll make them available if people are interested in reading more about them. And as I said, we try to include papers in different disciplines because these ideas have evolved over time in different disciplines. All right, so I think I have about 10 minutes to talk about proximal causal inference, which is about this idea of debiasing. So what I'll do is I'll describe the basic framework. If I have a little bit of time, I'll go over an empirical example, and then one slide for the conclusion. That will hopefully take no more than 10 minutes. All right, so let me skip right to, I'm going to skip this example, let's get another example. Let me talk about the actual statistical technique, right? We're all statisticians, so I'm making all these claims. Let me give an example where this is hopefully easy to understand. I want to make one point very clear here. I'm going to describe things under linear models. Well, understand linear models. This is nothing but an omitted variable problem in a regression analysis. From that perspective, if you don't care about causality, just think of that. Now, the regression where you're interested in the association between A and Y conditional on U, it's a linear regression, but you don't observe U. So you run an analysis of Y and U. If U is associated with both A and Y, U will go into the residuals, right? And that invalidates OLS as an unbiased estimator because you have residuals now correlated with your treatment. So if you don't care about causality, just think of it as that problem, omitted variable problem that I actually care about an adjustment, but I don't observe the variable in adjustment. And what I'm going to argue here is that if you have a pair of negative control exposure and outcomes, you can correct for that bias, okay, on the linear models. The larger point I want to make is everything I'm going to say here hold actually non-parametrically. So the linear model is nice and transparent. You can see what's going on. But the idea actually generalizes to completely non-parametric models that do not rely on linearity. And this is important because survival analysis, we use nonlinear models. Quantile regression, we use nonlinear models. Binary or count or polytomous outcomes, we use nonlinear models. Okay. All right. So what's the idea? I'm using this weird notation, but it's basically a number of times I'm going to like regress y on A, v1 on v2. And the idea is any such regression, it's a linear regression of v1 on v2. That's how you should think about it. That's like the code in R. The coefficient for that regression, the coefficient for v2, well, in general, it's going to be non-zero for one or two reasons. One of them is if v2 causally affects v1. And the other one is if there's confounding between. There's nothing else that explains an association in this setting. Either one causes the other, and v1 happens before, or v2 happens before v1. I should change the index, right? What v2 affects v1 causally, or they're correlated because there's a third variable that connects the two. And it turns out linear regression, the coefficient of that regression is the sum of the underlying causal effect, v2 affects v1, and the confounding bias. Causal inference is basically trying to get rid of this confounding bias, or omitted variable bias. Okay? All right, so I have here a number of coefficients, and if you're familiar with path analysis, I'm going to use the nomenclature. I'm going to have a gamma AU here corresponds to the association between A and U, beta YU, beta WU, alpha YA, of all those regressions, pairwise regressions. That's the nomenclature. And so the idea is, if I were to regress Y on A, everything here is causal. These parameters are actually capturing on the linear model that called that pathway. That's the pathway analysis. So if I were to regress Y on A using my favorite software, I would get a confounding estimate, which will be the underlying alpha YA. That's this guy. But it's masked by the omitted variable, which is the association between A and U, and the association between U and Y, the product of the two, because you just basically trace the path. And so you get that regression parameter is the confounding, the treatment effect plus the confounding. And the confounding is the product of gamma AU times beta YU. Does that make sense? So we're going to play this game over and over again, and we'll see that we'll have enough degrees of freedom to adjust for the bias. And the goal is to estimate this from the data. If we can estimate this from the data, I can convince you then that I can the bias by just subtracting. Nothing more than addition. Does that make sense? Just simple linear models. All right. I can likewise run a regression for W on A, and it's going to be the coefficient between A and W, which of course is 0. Because W cannot be causally impacted by A because W is the negative control outcome. I'm assuming we have valid negative control outcomes. We can poke hole into that later on. Okay? And so all we get from that regression of W on A is just bias. And the bias traces from A to U, and to U to W. And that's exactly what I said earlier. This is why we can use them to detect bias. Because it's a clean bias estimate. Okay? Now, I can run the two regressions, but unfortunately, this doesn't capture this guy. It would be nice if it did, then I could just remove it. I get an estimate of the bias and I remove it. There is, in fact, a method that assumes that it's the same, and that's exactly what we call difference in differences. That the effect of U on Y and the effect of U on W is the same. And this may be reasonable if W is a measurement of Y before the treatment. because they will be on the same scale and will be, if not too much time has passed, you can have a continuity argument that says that that effect is stable. And so that's what people do, and they call it, they have a fancy word, they call it difference indifferency, because all you do is you regress y on A, you regress W on A. Those can be thought of as two differences, the association between A and Y, the difference in means, and you take the difference. Thus the name difference in differences. Okay, yes. Oh, 5 minutes. Oh, really? Okay, I'll speed up. Okay, so we're not going to make that assumption. If I made that assumption, then I will be done because beta WU would be equal to beta Y. Okay? All right, so I'm going to speed up a little bit. Now I'm going to look at, that was using the negative control outcome. Now I'm going to do something very similar with negative control exposure. I can regress Y on A, that's what we did before, and I can regress Y on Z, the negative control exposure, and it's also a pure bias that traces the path from Z to Y. Again, I can't subtract them because it's not a clean estimate of the bias, unless the association between U and Z is the same as the association between U and A. That might be reasonable in certain cases, like air pollution, where we're using the post-outcome measurement of air pollution. In general, it will not make sense because they may be completely non-commensurate outcomes, maybe on completely different scales. So we don't want to rely on that assumption in general. All right, so what are we going to do? Well, note that I can rewrite the association between Y and A in terms of the association between W and A, because their biases are proportional. They share a gamma AU, right? And so what I can do is I can simply replace, take WA and then plug it here, and then just correct for the proportionality constant unity. This is just algebra. But I can't learn this from the data by just looking at Y and W. The goal of Z is, in fact, to be able to learn the proportionality constants. Does everyone see what's going on? I literally just plot WA, which is gamma AU times beta WU. But I need to turn into gamma AU times beta YU, so I need to divide by beta WU and multiply by beta YU. Okay, I can run the regression on the left-hand side, get that coefficient. I can run the regression of W on A. I know they're linearly related, but I don't know what the slope is. Okay, and so the point is that I can learn the slope by running the regression of Y on Z and W on Z. That was the second thing that we did. Getting the two regression parameters and then taking their ratio. And because the two regression parameters have in common gamma ZU cancels and you're left with beta YU and beta WU. And so I'm fitting 4 regressions. My outcome on my treatment, I know it's biased. My outcome on my negative control exposure, my negative control outcome on my treatment, and negative control outcome on my negative control exposure. Combine the 4 regressions, and I get the correction. I get the correction. This is the bias. So I run my standard regression. I run my 4 regressions. I combine the coefficients this way. We went through the logic, and I simply subtract it, and I recover the causal effect of A on Y. Okay, I think I've run out of time, so I'm going to skip about 100 slides. That's very ambitious. Okay. And I just want to mention that there are many other settings where these methods generalize to. You could have multiple treatment. This happens when you follow people over time. And they can take a treatment on one day and not take a treatment another day. And you happen to have a cohort setting which have those data. So there you're worried about time-varying treatment and time-varying confounding, both measured and unmeasured. So we wrote a paper to show how you could do that. You might be interested in mediation analysis with hidden confounders. So mediation analysis, the idea is I have a randomized trial, I estimate a causal effect, and I want to understand the mechanism. So I have a bunch of mechanisms that I'm hypothesizing, for which I make a hypothesis. English is not my first language, as you can tell. And you want to decompose the drag vector. That's what we call mediation analysis. And so you worry about hidden confounding in that setting. You might also have a hidden mediator that you think you know what mechanism it is that you care about, but you don't observe it. You observe proxies for it. Okay? And then there are network studies where people are worried about homophily bias. So network studies are looking at peer effects. There's a very famous study that was published in the New England Journal of Medicine. And the New York Times had an article about it, which said that obesity is contagious. And that was because the study was based out of Framingham, actually, looked at, you know, if a person is healthy today, but they associate with someone who is not, what's the probability of them becoming obese? And claim that was a causal effect, that actually obesity spreads over your social life. Okay? And the concern in such studies is that actually people who tend to be friends tend to have similar lifestyle habits. And so is it causal or is it all because of this association that's confounding? And that's known as homomorphism. Okay? And so you can use these techniques to address for this. And then there's a method known as synthetic controls that has to do with looking at the impact of intervention where you have a single unit that's treated and no natural control. And so synthetic control is a technique that came out of economics that allows you to devise such effects in those methods.